Hello everyone, my name is Tianhang. I'm a master student at McGill University. Professor Sharmistha Bhadra is my supervisor. Today I'm here to talk to you about my conference paper, LC resonator-based flexible printed RFID for wireless potassium ion sensing. First, I will introduce the research motivation. As potassium ion plays an important role in many vital biological processes, a simple and cost-effective potassium ion detection technique is preferred for monitoring levels of potassium ion in food and drinking water samples. To solve this problem, I came up with the idea to design a passive RFID sensor fabricated with the printing technology. For my design, the entire RFID sensor is composed of a printed passive inductive-capacitive resonator and a printed ion-selective electrode (ISE). It utilizes a transformer with loose coupling between an external readout coil so that the RFID can receive power via inductive coupling. The operating frequency is designed to be 20 MHz. It has the advantage of lightweight, flexible, and cost-effective, as it does not contain any embedded integrated circuit and requires no power supply. Therefore, it has the potential to be used in low-cost potassium ion monitoring applications. Next, moving on to the RFID system description, an equivalent circuit diagram of the coupled RFID sensor is shown in Figure 1. The formulas for RFID series impedance, input impedance, and the reflection coefficient S11 are shown respectively below. Next section demonstrates the experimental setup and the results. Figure 2a demonstrates the experimental setup with coupled RFID sensor and the interrogator coil. A vector network analyzer (VNA) is connected to the interrogator coil via a SMA connector. A separated distance d equals to 2 cm between the edge of the interrogator coil and the sensor is maintained to avoid overcoupling issue. Figure 2b demonstrates the proposed RFID sensor prototype printed on a 5 mm thick polyamide film substrate using a Volterra inkjet printer. Noted that some extra jumping wire and conductive epoxy were printed on the rear side to connect terminals between resonator and ISE. The measured S11 and resonant frequency at the coil interrogator for different potassium ion concentration is plotted in Figure 3a and b individually. It exhibits a second-order exponential relationship between the resonant frequency and the potassium ion molarity over 1 millimole to 2 mole per liter potassium ion dynamic range. Based on the measurement, the RFID sensor achieved an accuracy of 0.0136 mole per liter over the dynamic range. The response time of the RFID sensor is less than 3 seconds. In conclusion, the results obtained from the experiment exhibit a second-order exponential relationship between resonant frequency of the sensor and the potassium ion concentration of the contact solution. A simple, flexible, and cost-effective printed RFID sensor for remote potassium ion sensing is presented. The last session here covers all the references cited. That's all. Thank you.